Great morning. So I'm going to talk a little bit about some of the projects we're doing. We're based in Oxford and we're designing autonomous systems, mainly vehicles. But actually behind the vehicles is an interest in propulsion systems, in making super efficient propulsion systems. And the question that we're asking ourselves when we go through the design process is, what happens when you add a super efficient system to an autonomous system? Can we create some really, really high value machines or devices and solve some big problems? Now, we are interested in looking at nature. It's bio-inspired. It's not biomimicry, which is copying nature. There's a quote that goes, owners relish in parrots copying what they say and see that as a sign of intelligence. I mean, copying is not the same as looking at the underlying principles. Here are some examples of copying where kind of let's make a dragonfly. We'll make something that substantially looks like a dragonfly, or let's make a car that looks like a fish. Actually, what's interesting is the underlying physics in that, and can that be extracted and applied to do something novel? If you go back to the beginning of flight, and we're focused on flying vehicles right now, that's exactly what the Wright Brothers did. They studied how birds fly. In fact, there was a huge, great fight at the time because the Wright Brothers used wing twist as the control and patented and stalled the whole process of the development of flight. But what's interesting about it is that they looked at the underlying physics and applied that. What's also, I particularly, particularly like looking at that period of flight because it's an example of an early technological introduction creating a whole sort of chaos of solutions, which is kind of what we're seeing right now with AI. So, the Wright Brothers came up with the Kitty Hawk, but at the same time, there are all sorts of other designs which everyone thought were entirely sensible. But of course, now we sort of know what aircraft should look like. At the time, they all thought that's what they should look like, and each one of them had money behind it. The winning design, interestingly, was not the Wright Brothers. It was Glenn Curtiss who figured out how to use the aileron and figured out how to add a motor, which is a kind of salutary lesson. Also, right early on, people were building drones. This is 1902. It's called the Kettering Bug, and it was designed for the First World War. Incredibly ingenious process. They counted the number of rotations of the propeller to find out how far it was going to go, and then it dropped the wings and dived. It was kept under wraps until World War II. Now, this is a picture of the Wright Brothers in their workshop, and this is particularly poignant for us because we use computational methods a lot, but the problem is when you're making stuff, it doesn't yield very much data. So the question for us and for thinking about the impact of AI on design is, at what point does it become useful? We spend a huge amount of time in the lab designing things like wings, and the number of variables that go into designing wings is nearly 20. Each time we want to create a new set of variables, we need to build a new wing, so we are struggling to produce the data. What we're finding interesting is that it's very, very useful as a tool for fine-tuning, but for design, it's a creative process and really, really hard to deal with. So I think there's a sort of twist on the Moravec Paradox. So some of you may know the Moravec Paradox is a conjecture that was put out in the late 1980s by Hans Moravec, who's professor of robotics at Carnegie Mellon, saying that the paradox is that essentially that the tasks that we view as difficult and complex, which are largely computational, like winning games and playing games or solving mathematical problems, are actually in evolutionary terms enormously simple. But the simple tasks like perception and movement are actually enormously complex, both computationally and from our point of view, from a design perspective. So how do you make something that moves around the world simply and elegantly like the animals do? And it's interesting to me that the computer, or the robot he's got there, has got Meccano wheels, very, very clunky way of moving left and right and forward and backwards. Nothing like the elegance of the legs that we are blessed with. So we've been studying bird flight and looking in a lot of detail at the techniques and strategies that birds use to soar super efficiently. The feathers at the end of their wings are highly relevant. And some of you who follow F1 will notice that the front foil on an F1 car over the last few years has got lots of little fins on it. They are actually copying the aerodynamic gain that the birds have managed to get and applying it to their designs. Now, we're building a couple of vehicles that I can't show you too much about them because they're funded by DSTL. But the first one is using soaring techniques to basically design a system that replaces a helicopter. This is a scenario that we put together, which illustrates using a parachute system. The interesting thing about it is that the computational fluid dynamics that goes into the design of these systems is super relevant to getting the maximum efficiency out of it. And we're beginning to use these techniques, using some AI techniques to design the wings and optimize what we're doing there. And this is just an image of complex flow dynamic. The problems we're solving with this are things like building an air bridge, and there's a whole host of issues, really gnarly world issues about delivering stuff. And the problem with delivering stuff by air is that typically if you use a helicopter, it's a massively high value asset. It costs almost £2 million to train a helicopter pilot. The asset itself on the top left is about 30, 40 million pounds to buy. Delivering water, it costs almost nothing, but absolutely vital and essential to the people that are receiving it. And there is a vast array of activity worldwide involved in dealing with that problem. And we're finding that by focusing on these super efficient systems, we're able to provide a solution. The next vehicle that we're working on is really looking at how you can make a tiny UAV deal with a gnarly, nasty real-world problem, which is that it's really windy outside. And what happens when you make small UAVs is that they're fine when the air is still, and they're brilliant at going up and flying around and taking pictures, but when it gets windy, they get blown around. And so our background, or my co-founder's background, has been studying dragonflies, particularly interesting creature because they're territorial competitors, and they've been fighting with each other for 300 million years and optimizing their flight patterns. And they've come up with a fantastic design, which is better than almost all the other insects. In fact, they are the world's most successful predator. This is a CGI of the vehicle we're designing. It's got some accuracies and some inaccuracies in it on purpose. But just to sort of go through how AI is relevant to what we're doing, we are using learning techniques to manage the control system, to design the wings, but also to do the navigation and so forth. Turns out the control system for a tiny thing is almost as complex as an F-35, and we've got some of the engineers from the F-35 program helping us out. Not quite sure what's happened there. Anyway, I'll just carry on without the slides. There we go. So there's a nice picture of fluid dynamics behind flapping propulsion. So the massive challenge for us is to figure out at what point using AI becomes a relevant design tool. And so we're using techniques whereby we investigate flow patterns in a smoke chamber. We create a laser box around the smoke chamber and then use visual techniques to turn the smoke particles into points in 3D space. We put that into a computational model, and then we start asking questions. So, what happens if we change this model? What happens if we change that parameter? But it's a brutal and hard process because you go through that, and then we have to go back into the lab, get on the bench, and try and make something that is accordant to the model. But what's interesting from our point of view is that as we narrow in on this, we're able to make a device which is truly going to change the way in which little UAVs, in fact we can scale them up, fly around. We're also using CGI techniques. I spent a number of years running a games business and using some of the games engines to design the aerodynamic performance and analyze our navigational capability, design the visual systems, and so on and so forth. So truly what we're doing is bringing together old-fashioned design techniques, which are in the lab with glue and so forth, with the latest that we can deploy in terms of AI and so forth. The interesting thing about the little UAV we're designing is that UAVs are brilliant for flying around and taking pictures, but they are limited by the aerodynamics. and tend to either fly fast but not very long, or slowly for a bit longer. What we're doing is going to be almost 2 to 3 times more performant in that respect. But the interesting thing is when you compare that to what nature is able to achieve, a pigeon, an ordinary pigeon, for instance, which weighs about slightly less than a DJI drone, is way out there in terms of performance. And this is a video which will, I hope, make you respect and admire the pigeon more than we all normally do. This is a car driving down the Autobahn at about 100 kilometers an hour, and there's a pigeon there flying along quite happily, and it can do that for about 1,000 kilometers, by the way. And there is absolutely nothing that we are able to build that can come anywhere close to that. And that's why we're interested in looking at how nature moves. Thank you very much.